Linear versus exponential models, part 2. Let's jump right in. The half-life of a radioactive substance is 1 day. That means each day, half of the substance has decayed. Suppose you have 2,500 grams of this substance. Is this linear or exponential? Now, there's no percentage given. There's no constant number given. But when you think through, let's just start with 100 for easy figuring. If it's half-life, so the next day there's 50, and then 25, and then 12.5, and then 6. That's minus 50, minus 25, minus 12 and a half. That's not absolute. So we know this has to be an exponential. And what I want you to think about is half-life means 50% decay, right? 50% is leaving each day. So really, they do give you a percentage. They just give it to you in that it's half-life. So 50% decay. Now that I know that, and we know it's decay, so that means we are going to do our exponential model of y equals initial value, 2,500, 1 minus, because it's decay, 0.5 raised to the x. Simplify inside, so y equals 2,500 times 0.5 raised to the x. So half-life gives me a 0.5 in the middle. So we have our formula. How many grams of substance will be left after 4 days? Well, x represents the number of days, so we know that x equals 4. So I substitute that in. 2,500 times 0.5 raised to the 4th power. Order of operation tells me to do the exponents first. Exponents, that's a new word. Exponents go first. So 0.0625, multiply that then by the 2,500, and after 4 days, we have 156.25 grams of this substance left. Next, Sarah has loaded a prepaid phone plan with 500 megabits of data per month. Do people still do that? I don't even know. She likes to upload pictures to Instagram. In fact, that's all she does with her phone. I know people like that. From experience, she knows that each picture uses 2.05 megabytes of data. Linear or exponential? What do we know? We know that the starting point, the initial amount of data she has is 500 megabytes. Each picture uses a number, 2.05. It's a number. That's absolute change. That's slope. That makes this linear for all of the reasons I just said, right? It's based on the constant change. Each picture is 2.05 slope. So if I know my initial amount is 500, that's my y-intercept. I know my slope is 2.05. I can write a model. Y equals 2.05x plus 500. Nope, that's wrong. What's wrong about this? Well, the 2.05 should be a negative because it uses that much data. If I start with 500 megabytes and I use 2, it has to go down by that much. So make sure it's negative 2.05 x plus 500 because we are using data. Important to catch those kind of things. So we have our model with a negative sign. Use your model to calculate how many megabytes are left after 150 pictures are posted. So x is 150. So I substitute that in. Y equals negative 2.05 times 150 plus 500. Multiply first. So y equals negative 307.5 plus 500. We add those two together, and we end up with 192.5 megabytes of data left. Let's go to letter D. Use your model to determine the maximum number of pictures Sarah can post in a month. Well, how do I do that? Well, think about what Y represents. Y represents the megabytes remaining. So if we're trying to figure out if I use all my megabytes, that means Y would be 0, right? I would run out of megabytes. So I want to figure out when does my equation equal 0? Okay, we can do that. Subtract 500 from both sides. So I get negative 500 equals negative 2.05x. We divide both sides by negative 2.05. And when I do that, I get x equals 243.9. That's the max. Now, you can't do 0.9 of a picture. That doesn't work. So would I round to 244? Question mark? No, because that's too much. If I go up at all, I'm over my limit. So I have to just round down and say, I can do 243 pictures. That's it. I'll have just a teeny tiny bit of megabytes left, but not enough to do another picture. All right, let's do one more. Which growth pattern in the table is exponential? Which is linear? And how do we know? So we have time that goes from 0 to 4, and we're trying to look at future, classic, and standard. All right, so I always check for linear first when I'm looking at something. So like, what is the common difference between 19 and 20.38? So 20.38 minus 19 gives me 1.38. Then check the next one. 21.76 minus 20.38. 1.38. Oh! If I, 1.38, yep, this is linear. The first one is linear, and we know that because it has a slope of 1.38 based off what I just know. Okay, great. I love this for us. Let's look at the next one, classic. Okay, 9 to 15. Well, 15 minus 9 is 6. Then we go to the next one. 24 minus 15 is 9. Okay, it is not linear. Not linear. So then we check exponential. Do you remember how to check for exponential? We divide. So I'm going to start by taking 15 divided by 9. And when I take that, I get 1.67. Perfect. Love this for us. Then we go to the next one. 24 divided by 15. And when I put that in, I get 1.6. Well, let's just do one more for fun. 39 over 24. Does that yield 1.625? What? These are all different. So it's not linear. It's not exponential. It's nothing, right? It is neither linear nor exponential. That happens, y'all. Sometimes things are just things. All right, let's do the last one here. So I check 17.5 minus 7 is 10.5. Right, we're checking for linear. 43.7 minus 17. Whoa. No way. That's not even close to being linear. Okay, so it's not linear. Okay, so let's check exponential. So 17.5 divided by 7. Well, what does that give me? 2.5. Okay, 43.75 over 17.5. What does that give me? 2.5. Oh. Check them. Yes, they all work, so we know it's exponential with a growth rate of 2.5. And that, my friends, is how you go through and check if it's exponential or linear. I always check linear first, cross that off because I think it's easier. But, you know, you're subtracting to find the difference with linear. You're dividing to find the rate there with exponential. And you kind of celebrate when you find something. Thanks all.